Okay, excellent. I think we are now live. And again, just a quick confirmation that you can hear me fine and that the screen is visible.
Yes, ma'am, you're audible.
Okay, thank you. All right. So yesterday, we stopped by saying or making the following claim. We said that if you are looking at the game, which is a sum of individual NIM games or is equivalent to this combined game, then that in turn is equivalent to the NIM game with a single heap, where the size of that heap is given by the XOR of these individual numbers. And recall that we're taking the bitwise XOR here, which means we write down each of these numbers in binary, line them up, and column-wise, just take the XOR of all the bits in each column. And recall that the XOR is basically the parity. So when you're doing a XOR of 0, 0, 1, 1, that's a 0, and it's a 1 otherwise. That generalizes to any number of bits. It's a 1 if the number of ones is odd, and it's a 0 if the number of ones is even. Now, yesterday, what we did show is that if the XOR of these numbers is 0, then that's this game here is a P, and therefore this equivalence makes sense. And if it's greater than 0, we said that this is an N, and that's something that we proved. So in some sense, that was a sanity check that the label is reasonable, but why is it exactly equivalent to this particular game or this particular label? That is something that we did not argue yesterday. And even now, what I'm going to do is sort of give you a framework for how to argue this, but we'll probably not go through every detail in the interest of time. But I do think that the details are intuitive, just a matter of writing down a couple of additional lines in each case. So if you remember, one convenient way of arguing the equivalence of two games is to say that their sum is P. So remember, we said that G is equivalent to H if and only if G plus H is P, the outcome. And this is something we've shown before. So one way to show the equivalence of these two is to show that their sum is P. Say that the outcome of this game here is P. And to say that something is P amounts to saying that every child is N, right? That's when you are P. So a state is N, on the other hand, if it has a P child. So basically, what you want to say is that no matter what game you go to from here, you can flip it back to a P. And another useful thing to remember is that by the mimicking strategy, the outcome of the sum of two games that are exactly the same is also a P. So essentially, the idea will be that when you look at the move that is being made from the game that we are currently in, this game here at the top, we're going to say that, well, the current player is going to pick one of these games to move in. And what we will do is try to restore the state of the game, the other game, to match up the one that was modified, or to modify the modified game further so that it matches the state of the unmodified game. Those are the two cases that we will be in. So for example, it's possible that the first player chooses to play in this game. So let me maybe label these games here. So let me call this game A and this game B. So one case is that a move is made in A. And if you look at the XOR of the resulting heaps, so some Ni changed to Ni prime. And let me call this XOR here, let me give it a name. Let me call it Q. So if the XOR of the new heap sizes turns out to be less than Q, right? Then what you can do is, well, this is just a single nim heap of size Q. So you can reduce it to whatever this new XOR value is. And then you will have a resulting game. So after 2 moves have been made, so the current player makes a move in A, reduces Ni to Ni prime, right? And that leaves you with a XOR value which is less than Q. That's the case I'm considering. Then the response of the second player would be to take Q and remove as many sticks as they need to remove to make the new pile match up to the new XOR. So let's say that this new XOR value is some Q prime. Then all you do is remove some sticks from here so that the resulting heap has size Q prime. So you'll have a game that's a smaller game, and you're left with the two games being identical again. And here you can invoke the induction hypothesis to say that that's a B state because you're now dealing with smaller games at both ends, right? Or the overall game is a smaller game. So that's the approach that you would take in this case. But you could also have a very similar situation, except that the XOR could have gone up. Okay, it's just a spacing constraint. I'm going to say this case 3 here. So what if Q prime is greater than Q? Well, we are not allowed to add sticks to our nim piles. So in this case, the second player should not be trying to attempt a move in B. Let's leave the heap Q as it is. But it turns out that if your N1 up to Ni prime and then so on and on up to Nk has a XOR value that is larger than Q, then you can modify one of the heaps again to bring this file back to Q. So you can go from Q prime back to Q in the game A itself. So you stick to the same lane as the first player and try to revert this back to Q. And the logic is very similar to what we used last time. So if your modification caused the outcome to increase, that means that the most significant bit flip, or the bit that changed, must have been a change from a 0 to 1, which means that there must be some pile here, which at that most significant bit was in fact a 1 and everything. So what you can do is work on that pile, flip that bit to 0. So you're guaranteed to go to a smaller pile. And you're also basically, you've started the work of coming back from Q prime to Q. Okay. So the way I developed some intuition for this was by working through a couple of examples. So I highly recommend doing that in case this is getting too abstract. Okay. But the idea is that, first of all, when you're modifying a collection of nim heaps, there is no guarantee that the XOR will also reduce. So even though the number of sticks have reduced, the XOR value may actually increase because you may have flipped a 0 to a 1. And that's entirely possible. Okay, so for instance, even in this simple example where let's say you have 2 piles with 1 stick each, currently the XOR is 1 plus 1 is 0. But if you get rid of one of them, then you get a 0 plus 1, which is a 1, right? So the XOR value may have increased, but in this case, notice that you can bring it back to a XOR value of 0 by also removing this other heap, the stick in the other heap. So that's kind of the strategy. And I'd also recommend working through slightly more non-trivial examples to sort of get a feel for what's going on here. But again, the idea is that if the new XOR sum is less than the original XOR sum, then attack the other game and reduce it to now a common XOR sum, which is Q prime less than Q. But if it is bigger, then continue working in the same nim game and make things right again by making everything Q. Okay. What's the remaining case? Well, it could be that a move is made in B. And here it must be that you are taking, well, you only have one file which has Q sticks. So you must have changed Q to some Q prime less than Q. And now you apply the same logic as before to say that, okay, if Q is changing to Q prime and Q also happens to be the original XOR sum, and you have now changed it to Q prime, so you just stare at both Q and Q prime. So let's say Q was this binary string. This was the binary representation of Q is this bit string. And you changed it to some Q prime, which is less than Q, which means that if you look at the binary representation of Q prime, it's probably tallying with Q up to some point. But because it's less than Q, the first change that you encounter must be a 1 flipping to a 0. The first change walking from the left cannot be a 0 flipping to a 1 because then Q prime will be bigger than Q. So look at the first bit from the left that changes. Look at the most significant bit that changes. That flip must have been a 1 to a 0, which means that when you're looking at the sum of things that was, so originally this was Q, which happened to be a sum of all the ni's. So look at this column again. It has an odd number of ones because the original XOR sum was 1. And if it had an odd number of ones, then in particular, it had at least 1. So go to any of the piles that has at least one, that has 1 in the ith bit when you look at the number of sticks in that pile as a binary number, okay? Or you look at that number in binary. So this is the pile you'll be working with. You will change this to 0, which guarantees that you're going to a smaller number. And the rest of it is again like a subtraction thing, just like we argued last time. So you change it to match whatever this new Q prime is. So you can continue the game in A. So if the first player moves in B, then you can, the first player moves in B, changes this Q to Q prime. Then you make a move in A so that the XOR sum becomes Q prime. And once again, now you're in a situation where you have smaller games and their equivalence is established by the induction hypothesis. And in this pair of smaller games, you have a P state again, because it's a Q prime and Q prime. Okay, so yeah, so you can think of it as a mimicking thing, or you can just directly say that the induction hypothesis guarantees us that these two games are equivalent and hence their sum is P. So either argument should be fine here. So that's at least a template for how you might argue that if you're looking at a combination of these nim heaps, N1 through Nk, then the label associated with them is the XOR sum of the Ni's. And this is nice because it saves us the trouble of generating all the children. Because if we tried to figure out the label using the game tree approach, what we would have to do is look at all the possible states that you could go to. So you'd have to generate all the children. And the number of children is going to be at least summation Ni, because each of those, actually it'll be more complicated than that. But basically, yeah, actually, let's just count how many children there are going to be. So if your current game is a collection of nim heaps N1 through Nk, then you can pick any of the Ni's and change it to something that is less than Ni. So essentially, you do have summation Ni many moves, I believe. So a move is determined by which heap you pick and what is the moves that you make within that heap. So the total number of possibilities would be summation Ni, because in heap 1, I have N1 options, and heap 2, I have N2 options, and so on. So you'd have to generate that many children and actually look at what their labels are. And now, if you don't know what their labels are, you'd have to go further down this rabbit hole, and that can be pretty expensive. This is more of a one-shot calculation, which tells us that, okay, you can, if you know that you're looking at this particular nim game, then you can XOR the numbers and you have the label for the combined NIM game. Of course, if you are not in a game tree of a NIM game and it's a different game and you don't know that it's a decomposition into games whose labels you already know, then of course this is not going to be very helpful. But at least as far as the NIM game tree is concerned, the numbers compute nicely. And if somebody just gives you a state of a NIM game, then this XOR formula is kind of useful to derive the label, to derive which equivalence class a particular NIM game belongs to. Okay, so I hope that that made sense. And I'm going to spend like the remaining 15-ish minutes that I have on introducing some new games. So we're going to shift gears here a little bit. And if you're following along with the book, then I'm moving to section 8 and the 0th chapter, which is called Other Impartial Games. So here, I think we're just introduced to a few more rule sets. And this will also give us an excuse to go over what is called a strategy stealing argument in the context of one of these games. So let's see if we can get to that point. So one of the first new games we're going to talk about is this game called Avoid True. This is a game that is played on a Boolean formula. So the playground has a bunch of Boolean variables, x1 through xn. Just think of these variables that take values in 0, 1, or if you prefer, you can say true and false. And what you're given is that, well, initially, all of these variables take the value false. Just draw out an example because that will probably be the easiest way of understanding the rule set. Okay, so we have a bunch of variables. Their initial values are all false. And what else are we given? Well, we are given a collection of, essentially a collection of subsets over these variables. Okay, so here's one example. So for those who are in the know, this is essentially a monotone CNF formula, but you don't have to worry about that if you're hearing that for the first time. Okay, think of it as a collection of subsets of these variables. These subsets don't necessarily have to be disjoint. They can be overlapping as they are in this example. So for instance, x2 is common to these sets, x1 is common to these sets, and I think that's all the overlaps we have here. So avoid true is to say that we don't want this formula to evaluate to true. So when does this formula evaluate to true? Well, a set here, an individual set, is going to be true if any one of these variables is set to true. Okay, so this is true if at least one of the variables is true. So for example, if I change x1 from false to true, that will end up satisfying these two sets. These two sets become true. The formula becomes true if all the sets become true. Okay, so you don't want to be in that situation. So if you are the player for whom you cannot flip any of the falses to trues anymore without making the whole formula true, then you lose the game. Okay, so let me just make the rules explicit. On your turn, a move is switching the variable from false to true. So you can pick any of the false variables and pull the trigger and say, I want to make it true. And this will probably have some impact on the formula. And here, for example, let's say in the first turn, the first player says, I want to flip x1 to true. That has the effect of making the first and the last sets true, or sometimes these are called clauses, so I might use that term as well. So it's going to satisfy, that's another term that's useful. If a set becomes true, you say that it's satisfied. So set is easy to satisfy. You can satisfy it by setting any of its variables to true. And at this point, what does the second player do? The second player knows that setting x2, x3, or x5 would be dangerous because it would satisfy this set here in the middle. And once that set is satisfied, then this, the whole formula is satisfied, the whole, the entire collection, like we're basically done, right? And if the second player does make one of those moves, well, then that actually leaves the first player with no moves now, right? So in some sense, okay, so let me, okay, so I think that's how we've been normally playing, but I just realized that we also have this rule. A variable cannot be flipped. So that's actually not a valid last move. So a variable cannot be flipped if the flip causes the whole formula to become true. So the highlighted flips here are actually flips that the second player cannot make, because the moment those flips are made, the whole formula becomes true. So in some sense, these are forbidden flips. If we were doing, a different rule set could also be that, you make your moves, if the whole formula becomes true, then the other player has no moves left. But that would probably, so the first person to make the whole formula true would be the winner. That could be one rule set, but that's not the rule set we are looking at. Here, the variables that make the whole formula true, if flipped, are out of bounds. You cannot flip them. So currently, x2, x3, and x5 in this example are untouchable. You cannot flip those. So you can either move to flip x4 or x6. And both of them just increase like the number of true literals inside the third set. And the second player can choose to flip either of them. The third player will flip the other one. Sorry, there's no third player. It goes back to the first player who flips the other one. So the second player on their turn can choose to flip x4. And when it goes back to the first player, they'll actually have no choice but to flip x6. And now we're stuck. There are no more moves to be made. So the second player in this particular case would lose. So that was actually a good move for the first player. But the first player could also, just to get some practice with the game, choose to flip, say, x4. What effect does that have? But if the first player flips x4, then that makes this set true. It doesn't affect any of the other ones, right? Now, the only flip that is forbidden for the second player now is x2. Because if you flipped x2, then you would satisfy both of the first couple of sets. And that would mean satisfying the whole formula. So x2 is forbidden. But you could do any one of the other ones. And in particular, for example, you could continue playing in a manner that does not change the set of satisfied sets. So for example, if you choose to flip x6, as the second player. So you're flipping it so it becomes true. Then nothing changes because neither the first nor the second clause had x6 as a variable in them. And at this point, the first player, no matter what they do, they will end up satisfying at least one more set. There is, they could choose to play inside the third clause and pick x1, but x1 also appears in the first set. So let's say they choose to flip x1, then they end up satisfying the first set along with the last one. And at this point, there are, well, let's see. If there are other moves to be made, well, x3 and x5 would both trigger the second formula. So those are again out of bounds. And once again, the second player is stuck. And if the first player in the previous move had not chosen x1, but instead, let's say they'd chosen something like x5, then the second player would still have the opportunity to play x3, for example. And then the first player would have been stuck because they couldn't have picked anything more without satisfying the first clause as well. So those are some examples of gameplay with avoid true. Hopefully the rules are clear. And you can spend some time playing. You can also spend some time trying to analyze this game if you like. But I'm going to move on to at least sharing a couple of more rule sets with you. And not sure if we will have enough time to prove anything about these games. We may have to come back to that next time. But nevertheless, let me at least describe to you a couple of more fun games. So here's node Kyles. There are other variations of this as well, but the one that we're going to talk about now is node Kyles. Here, the playground is a graph. So again, a graph is probably a familiar object for most of us. If not, it's just essentially think of it as a relation on a finite set. So a graph is given by a set of nodes or vertices, V and E is a subset of V cross V. So that's just like the edges tell you which pairs of vertices are in a relationship. We are going to be looking at symmetric relationships here. So if a pair of vertices U and V, U comma V belongs to E, then V comma U belongs to E as well. If it's not symmetric, then usually this visual representation will have arrows to tell us which way the relationship is going. So in particular, for instance, if UV is in E, but VU is not in E, then you'll have typically an arrow pointing from U to V to remind us that that relationship is one way. But like I said, we'll be focusing on the symmetric case here. So no arrows in my picture. Okay, so how does this game go? Well, you take turns picking vertices from the graph. And the rule is that, well, we never want any of the chosen vertices to be related to each other. So that's our constraint, which means that if, for example, the first player picks this vertex here, then these vertices are now forbidden because we cannot have two chosen vertices have an edge between them. That's kind of the heart of the matter here. So the second player can now move on to, we denote the second player's moves by blue. So for instance, if they pick this vertex here, then all of these guys are now forbidden. And now notice that picking any further vertices does not create any new forbidden vertices. So the first and the second player will just alternate. And so the first player might pick this one, the second player picks this, the first player now picks the other highlighted vertex, the second player picks this, so now the first player is stuck, and therefore they lose the game. So the way I think this is presented in the book is that these vertices that are chosen, the vertices that are forbidden are removed from the graph. So you can actually, sort of delete these vertices as you go along. I find it just easier to mark them as forbidden and keep the whole graph in sight as we go along. And again, the question would be, which player has a winning strategy. Notice that this is going to depend quite a bit on the structure of the graph. And all right, I'm sorry I wasn't paying attention to the chat a few moments ago. So let me just hold this for a second and go back to this game. The question was, how are these sets chosen? Well, that's actually the input. So the game is a collection of sets. And given a collection of sets, you want to figure out what's the optimal play. It's similar here. You might ask, how does the graph structure come about? Well, that is the input to the game. So every graph is a different game. So depending on what the graph looks like, you're going to have different styles of play. Different players may have winning strategies depending on how the graph looks. So for example, if the graph happens to be what is called a star, which is it has one vertex and a bunch of vertices just sticking out of it like that, and nothing else, well, then notice that the first player has a really good situation here because they can just choose to take this vertex out, and the second player would have no moves left. On the other hand, if the graph was, well, let's say it was a triangle, for instance, then that's a bad situation for the first player because, oh no, so this is actually the same as before. I want to create a graph which is a bad situation for the first player. And maybe it would work if we had a slightly longer path. The triangle is good for the first player because they actually, again, take out all the vertices no matter which vertex they pick. So actually, any large clique is very good for the first player because they can play anywhere they want and they take the whole graph out in one shot. So those are kind of trivial instances. But what about a path? Well, the first player could start here, in which case the second player can end it by picking this. So that would work for either of the middle vertices, or the first player could start at one of the endpoints, but that still leaves the second player with enough room to pick and kill the whole graph. So if you have a path on 4 vertices, then that's actually good for the second player. So yeah, right. So Akash is saying C4 should be P. Yeah, so I think a P4 is also P, and a C4, I think, for the same reason. Yeah, I think this works out pretty much the same, except that in this case, I would have to. Okay. It's probably easier to just do this again. That would be the second player's move. So yes. So C4, P4 are both good for the second player. Thanks, Akash. So, all right. So that's node Kyle's. You take vertices out and you take their neighbors with them. And the first player to get stuck is the player that loses the game. All right. I don't know if we have enough time to do one more game called Chomp. It's actually a really easy game to describe. So let me just leave you with the description, just in case some of you want to go and play these games later in the day. So, so at least simplest version of Chomp to imagine is that you're playing on a rectangular board. Think of it as a chocolate bar, and think of it as a grid. And on your turn, you get to pick a square that's still available. I'm saying still available because in general, squares are going to disappear. So I think in some descriptions, I've seen folks saying that the bottom left square is poison chocolate, so you don't want to pick that up. But everything else is very tasty and safe to eat. So on your move, what you can do is basically pick a square where you want to chomp into this bar. And if you pick this square, you basically get this whole piece. And that goes away, and you're left with a Okay, I should go back to not erasing full strokes. So this is what you're left with after you have jumped at a particular location. This goes away. And so you can pick another square, and that would eliminate these guys. Or if you picked this, that would be just that one square. If you pick this, it would be this whole thing out here. If you pick this, it would be this. If you pick this square here, then you take out this column and this row. So essentially everything that's available still to your top and to your right, all of that goes away. And that's the portion of the chocolate that you get to have on your turn. And one way that I think about this game is I want to maximize the amount of chocolate I get to eat, but actually you only win if you're not stuck. So if you can create a situation where the other player has no valid moves, which would be the case when you're left with just the bottom left square and nothing else to do, then that's when you win the game. So it's relatively easy if you just have one-dimensional boards, because you can just jump greedily. But on a more general board, well, if the boards have arbitrary shapes, I'm really not sure if anything meaningful is known. But at least if you start off with a rectangular board, you can argue that the first player can always win. And that's a cute argument, but it will still take, I think, a good 5 or 10 minutes to make sure that we go over it properly. So I think it's best left for as food for thought, no pun intended, and best left for our discussion tomorrow. So tomorrow we'll begin by arguing that if you have a rectangular board, then the first player has a winning strategy in Chomp. And we're going to look at a few more NIM variants before rounding off in this chapter. So that's kind of the plan. So thanks so much once again for joining me and for sticking it out. I'm going to call it a wrap at this point and open it up for discussions.